All right, pop quiz. Just kidding. Here we go. 7.3. Welcome back, everybody. In 7.3, the last section of chapter 7, we went from magnets to electromagnets to today's big idea is how do we actually go about producing electric current. Now, the cool thing about today's lesson is a lot of these pieces are going to wrap back around to ideas that we've already talked about. I'm going to try real hard over the next 40 minutes to call on every single person in the room. Cool. You might get called on more than once. Just be prepared. So, like, if I call you early, doesn't mean that you're done for the day. Cool. You guys still remember all your numbers?
Yeah. Wait. Yeah.
Where you put your phone?
Yeah. So there are some phones missing here, just throwing that out there. But right off the bat, we're going to talk about this idea and we're going to define it. It's super fancy sounding, but we're going to give ourselves this topic of electromagnetic induction. Electromagnetic induction. Now, I guarantee you have seen the word induction this year. It's been a while. There was one day in chapter 6 where I know that I was absent because my kid was sick. One day where you guys had to come in here and read the book. And it was in that electricity chapter. In there, I know for a fact that they mentioned charging by induction. And that may or may not ring a bell. Anybody remember what that meant? If I want to charge my phone, if I want to do it just, the good old traditional way, I will just simply plug my phone in. Okay, through direct contact, the current can then flow. Now, if anybody has a smartwatch in here, I also do. This does not have a place to plug in. Anybody in here have a smartwatch? How do you charge it? So you don't plug anything into it though. So somehow the magnet, and it's magnetic, I assume. Somehow that magnetic that sticks to it, or the back of your iPhone, or like me and Sonny's phones can do the same thing because he has an Android as well. We can charge phones and watches and things like that without ever physically letting electricity move into it, right? Like we see that with magnets. If you've ever seen the fancy chargers for the phones where you just put it on the platform and it charges it, you're never plugging it in, but somehow you're getting electricity into your phone. And it's not like magically floating through the air. There's another idea, and it's called, what do you think?
Electromagnetic induction.
I like that, but the more, Sonny said wireless charging, you're correct. But more appropriately is this idea of electromagnetic induction. Now, sounds fancy, it's not too crazy. You guys know what an electromagnet is, I think. What's an electromagnet?
Solenoid.
Go on, so there's a solenoid. What is it?
Made from electricity.
Cool, current flowing through creates a magnetic field. Remember, two sides of the same coin, right? Okay, so as we're looking here, super duper easy to define this. Electromagnetic induction, super chill. This is just a current produced by a changing magnetic field. That's it. So, if you have a magnetic field that keeps changing, whether the poles are flipping or whether it's just the strength of it changing, electricity is like electrons moving, right? And electrons have a charge, and they're repelled or attracted to magnets, depending on what side it is. If I have electrons moving, I have current, and it turns out if moving a magnet causes those electrons to move, then just moving a magnet can produce current. By that magnet that you stick on the back of your phone, the back of your watch, whatever, there are devices in here that take that magnetic change because of the type of current that comes out of your wall and produces electricity to charge your watch, your phone, whatever the case might be. Now, as we look at this idea is pretty awesome, and it comes from two different places. When do you think the idea of wireless charging became known to humans? 2012, I'll tell you before that. 2000 before that. 1998 before that.
1997.
1970 before that.
1975.
Hold on, not zero. I'm getting do it again. When was the Tesla coil made?
1960.
Okay, so you're getting closer. Tesla, I think, was like 1870s and stuff. I'm never going to quiz you on dates and names and stuff. 1831 is when this was discovered. Before that, like 30 years before the Civil War, which is pretty awesome. 2 people have discovered this simultaneously, and whether or not they were like exchanging ideas, I don't know that. But one person discovered this in the U.S. Their name, didn't know this one, Joseph Henry. Never heard that name. I don't know, he doesn't get credit for it. On the other side of that, have you guys ever watched any spy shows and stuff?
Yeah.
Okay, let's say hypothetically that like I'm totally afraid of the government looking at like my phone and my personal stuff. If I turn my phone off, does that really stop them from looking?
No.
No. Is there anywhere that I could put my phone, like even if I take the battery out, like that's not going to suffice. It will not be enough to stop somebody like the NSA or any, it doesn't matter what country, any government agency of any like real country could still look at that stuff. So you can't just take the battery out. If you straight up break it, that'd probably do it, but you probably don't want to break your phone. What could I possibly do with it?
Throw it.
So tinfoil won't quite do it, but you're on the right track. Okay, have you guys ever heard of a Faraday cage?
No.
So it's like a little box of a particular type of metal that you can put devices in, and there's no way to communicate with the outside world. And I heard magnetic field and tinfoil box. They're on the similar page here. Now, turns out the idea of a Faraday cage, which if you were a spy and you were communicating with whomever, whatever government, you would put your phone, your stuff in a Faraday cage when you're meeting, because you don't want anybody to tap into the microphone, you don't want anybody to tap into the camera, any of that stuff. You need a way to prevent any information from being exchanged. So, Faraday, whether we go further into electricity or not, Michael Faraday is the big name with electricity. I'd never heard the name Joseph Henry. Faraday's name shows up all over the place with electricity. Okay, now this idea of electromagnetic induction is big, and it's really important if you want to have, like a global society. So, right off the bat, Sonny used this word earlier, we have a bunch of small, like main sections today. We're going to talk and define generators real quick. And I wish I had some of these old flashlights. You guys ever used a flashlight that doesn't require any batteries? They're kind of annoying if you give it to a toddler. You spin it, right? Do you guys know the magnets I'm talking about? Or the not magnets, flashlights, thank you. Okay, so what you're seeing there is a basic type of generator. That's it. Now they buzz and there's some stuff going on with it, but there's 2 ways that you can do this. I know that if I have a magnet and I'm moving it through a coil, like just moving it like physically through it, do you think that magnetic field is moving? For sure, right? Like it just moves along with the magnet. Are there things within that wire that are going to start moving because of that magnetic field? So if I wiggle a magnet next to some copper, the electrons within there are going to start wiggling and I'm going to get a small current, right? Now, what if I flip it? What if instead of moving the magnet, I had like a coil and I moved the coil? Would the coil then be moving through a magnetic field in the same way? Do you think the electrons inside of that would start to wiggle? And those wiggling electrons produce a current. So we can do it either way. Whether I'm moving the magnet or the coil doesn't matter. Electrons wind up moving and generate current in either situation. With that in mind, generators, as a simple definition, this is just a way to convert energy. Now, the old-fashioned ones that I'm winding up, what sort of energy am I using right now if I'm physically winding it? It's mechanical. It is my hand causing it, but it's mechanical movement. So a generator, all that this does is it converts mechanical energy to what lights up the light bulb in the flashlight? So what kind of energy? It's not mechanical anymore. It's not copper energy. Electrical. So from mechanical to electrical via, and if I use this word, do you guys know what this means? Via?
Never understood what it actually meant.
From or through, like as a result of induction. Now I'm not going to write the whole word, but if you want to be really wordy and write a ton, you can say converts mechanical energy to electrical energy via electromagnetic induction, and it's the same meaning. We're talking about electromagnetism. Okay, now in this, there is much more complex versions than this. I'm not going to draw the picture here, which is one of the huge benefits of this, but we will look at the picture. So, as we're looking at this, we're only going to deal with the super simple ones, and then we'll extrapolate beyond that, which is just make predictions based on what we've seen, and say that, oh yeah, this could probably be applied to a bigger situation. So we're going to take a look at a simple generator. Now, if you want to draw the picture, you can, but I can't draw this nice and two-dimensional. And let's see here. I'm going to steal this, and I'm just going to copy and paste off of my notes. And then we're going to look at some stuff. There. Okay. Is anybody like feeling as though you're going to draw this?
I will.
If you're just dying to, it's page 180. Now, as I look at this picture, it looks kind of like something we saw yesterday, I think. It looks like an electric motor, doesn't it?
Yeah, it looks like this thing.
Only one little tiny difference. When we looked at the electric motor yesterday, there wasn't a hand that was turning it. You had a battery hooked up, bless you, bless you. You had a battery hooked up that would make the magnet turn itself, and then you would connect your drive shaft, your fan, whatever here, and this power would turn the magnet, would turn this. Right? That's what we saw yesterday with the electric motor. Now we're just flipping it. Instead of hooking up a power source, we're now making this power source. And if we look at this just kind of, we see some fancy stuff. These are the brushes that we talked about yesterday with the electric motors. If I turn this, you can't see the inside, but when I turn my hand here, this dial, what do you think turns over there? So it's going to turn the drive shaft, which is connected to this here is not the magnet. What is this? It's like your coil. It's your solenoid in here. Now, there's a magnet that's sitting around, but check out what happens. As I generate this, I now have current being generated because it's moving through the magnetic field, just like we talked about just now. Now, there's some fancier stuff going on in here that if you're really interested, there's lots of YouTube videos that'll make sense of this pretty easily. If you want to make your own electric motors, they're not crazy difficult. But as I turn this, I generate current in this coil, which then flows through, and through some pretty fancy stuff in here, allows me to get the current to flow. Cool. Nothing crazy about that. Where things get a little bit harder to think about, we talked about, and I showed you guys yesterday with the compass and the magnet. When I turned it, it made the needle turn, right? Now, we commented and I commented about, like, you have to make it work at the right timing, and that's not our focus. What is our focus is one couple little basic ideas. I'm going to take this whole thing and move it over. Two little ideas that I don't care if you have the picture, but I'm referencing this picture, okay? So if you need to put it, page 181, if you need to see this. Cool. So, quick little comment. Every half turn that I make, do you agree that I get a different end facing north? So every time I make a half turn, I see that I'm going through that north to south cycle. So we're going to make note of that real quick. Each half turn, each 1/2 turn, the poles change. And when I say this, I'm going to hold off before I write any more. When I say the poles change, it's obviously not the magnet's poles, because what sort of magnet do we have there? Not yet, not directly. Permanent. Like that's just stuck there. It's inside of whatever. When I say the poles change, if this is side 1, right now it's on north, right? Half a turn away, where is it?
South.
South. So I see that those poles are changing with regard to the solenoid here. Now, as I do that, another half turn, they swap back and forth. So I'm just going back north to south is all that's happening. I know that I can move in a full circle, but north and south just keep switching. Okay, as that happens, the poles change and the current winds up doing something. If I switch this from north to south to north to south, what we don't see in this picture is the current's actually going back and forth. It's 1/2 turn, it goes this way. When it goes the other half of the turn, it's changing and it's pulling back the other way. So we're creating what kind of current when that thing spins?
Alternating.
We're creating an alternating current within it. It's really far out there, and this is some fancy engineering, right? Like people dedicated their life to developing this. This is the basic story of it. Okay, we have that happening. Current alternates. Now, am I going to ask, like, do you think it's fair that I explain in detail how this works? I don't think that's a fair question, because I would struggle to explain it in a nice, concise fashion. But if I ask what happens as these change, if I spin a coil in a permanent magnet, what happens? So it does spin, but what am I generating? Power. And what kind of power?
Stop asking me. I don't know.
I don't know. You keep answering. We're making eye contact. Carson, we made eye contact there. As I spin a coil inside of a magnet, it generates what?
Electricity.
Good. That's the right answer. I can see the light bulbs lighting up. Cool. Now, beyond that, we see this happening. In the U.S., this happens in a very specific way. And this will vary by country. In the U.S., when we're talking about this idea happening, the coil turns at, and you guys have seen this word, but I don't know if you know what it means. I'm going to write HZ. Hertz. What on earth does that mean? 60 hertz. You guys probably think, I know what I think of with hertz. What do you think of, Max?
Like a way to measure hertz is sound, right? Or is hertz? No, sound is decibels. Like to measure brightness.
So, kind of. You're thinking of a monitor, maybe? I'll tell you, sound can be hertz as well, just so you guys are aware. What do you think of with hertz? What do you think of, Vincent? When you see hertz, 60 hertz, first thing in your mind.
Kind of like 60 frames per second. Like
Ooh,
1.4.
frames per second. Anybody else think of a monitor?
I thought
Coins?
subwoofer. I feel like it's like money, bro.
I remember a bakery when I was little. You guys ever had a Hertz donut?
Yeah.
Oh.
I don't know if that
Hertz
joke
donut?
lands with it. You've never heard that
Oh,
before?
Hertz donut. Okay.
So you got little siblings. Don't be like overly mean.
Hertz donut.
But yeah, you ask your younger brother or sister, whatever. Hey man, you want a Hertz donut? Yeah, and you go. You say Hertz donut. It's like just don't really do that. I probably should have paused. I do not support violence. All right. So as we're looking at this, Hertz. You guys have most of you have seen this word. It turns out when you're looking at this, when we see Hertz, we're just thinking spins per minute is what we're going to think of with electricity. Now, we're going to go one step further. Every rotation I see north and south switch, right? In one spin, half the time it's facing north in the coil and the other half is facing south, right? So how often does my current change in one spin? Twice. If I have 60 spins, how many times does my current change? So right off the bat, when we have 60 hertz as our coil turns at that rate, we have current alternates how many times per minute? 120 times per minute. Now, this isn't the big focus, but just to check the math idea. What if it was 100 hertz? How many times does current switch per minute? 200. You literally just double it because every full revolution you see those poles be different location, right? Okay. Now, this is all fine and dandy. Any of those magnets that you would ever wind up or a radio, this is the essential of what you're going to see inside. Okay. Do we ever need more energy than maybe a flashlight? For sure. So, as we look at this, we're going to make one big leap. And it turns out it doesn't matter if we're talking diesel or nuclear, irrelevant. In this picture, my hand spins and it turns what? So the brushes don't spin.
Oh, wait.
The brushes stay here.
Slip.
What's connected on the other side of the slip ring? This is my coil, my solenoid, right? This is spinning. Now, is it possible that we create a mechanism that instead of the coil spinning, I make something else spin that does the same thing? I could spin the coil inside this magnet, or what's the opposite?
Spin the magnet.
I could spin the magnet around the coil, right? And it would produce the same effect. Whether this spins or this spins doesn't matter as long as I'm switching that north and south direction. Okay, with that in mind, we are going to move up in scale. So here we go. We have a simple generator. And now here's the part that I'd say matters to you. Large scale current production. Okay. Rather than turning the coil, which is fine and dandy, that works, we could turn the magnet. And depends on how strong you want this. Oftentimes magnets are really big and really heavy. So it takes a lot of energy to spin them. But I think it's less to have a single magnet than tons of coils lined up because you're going to have way more metal, it's way more weight. Okay, so here we go. We're going to draw a picture of a power plant and we're going to use that to make sense of this. What kind of power plant do you want?
Nuclear.
A nuclear power plant?
Yeah.
Okay.
That's sick.
You can draw, I mean, a tower there is fine. Why do they have these big towers? Is it smoke when you look at a nuclear power plant?
Yeah. Wait, what?
Mm-mm.
It's not smoke.
It's not smoke.
It's really toxic.
It's not toxic. It's not green. Like, check it out. We'll just Google real quick. Now, if one exploded, it'd be super toxic, obviously. Okay, so here it is. That's not smoke.
Oh, it's steam.
It's steam.
Same thing, right?
Oh, is it?
Steam is like precipitation or something.
How do you make smoke?
Steam is just water.
I don't know.
Steam is boiled
What?
water.
Yeah, this is water. This is water. This is fog. This is water. Yeah, I'm feeling pretty deja vu-y. Indeed.
Yeah, that is-
Random thing, we're not going to look it up. One of my favorite videos that makes my kid laugh, and I try not to just share facts about my kid all the time, but there's lots of videos where people take this and, like, you ever seen one of these towers come down or any tower be, like, collapsed?
Yeah.
No.
Can you imagine that this tower got collapsed?
Yes.
Okay, so there we are. There's videos where people will take this, and we're just going to look at it. I'm going to pause real quick. You want a quick brain break?
Yeah.
Okay. Here's our power plant. Now, I don't care if it's nuclear, coal-fired, geothermal. Oh, damn, it doesn't matter. Any of them do the same thing. If I have a heat source down here, and again, doesn't matter what it is, and we definitely talked about this in here. Say I have a big tank of water, and underneath this big tank of water, let's say we burn diesel. What's going to happen to the water in here? It's going to start to boil, right, first of all. And then once it boils out of here, what's it going to do? It's going to make steam, and where's steam go? Okay, there's the steam that comes out of our towers. We've not made electricity yet. We're about to, though. We've decided, and what we've seen is that I can generate electricity by spinning a magnet around a bunch of conductors.
Isn't there like a fan in there?
Gosh, there is like a fan in there, but we're not going to call it a fan. In here, we have a turbine. Cool. So, here's that part of it, and there's that part of it, and there's another one over there, and it's spinning. Now, these are heavy. These are heavy for sure. Now, hypothetically, let's say near this turbine, and you don't have to draw these, but let's say I have a bunch of coils, and this is obviously a small coil. Let's say I have a bunch of coil in there, and there's really a lot of them. What should I connect to that turbine to make it so that those coils are moving through a magnetic field?
What?
What could I connect to those fan blades that when it spins, makes a magnetic field move around those wires? Could you put that big permanent magnet on these? If we connect these big permanent magnets, as long as there's steam coming out of this, is that magnetic field going to move around this? And as a magnetic field moves around this conductor, what does it make? It makes electricity, specifically. This is how modern electricity is produced. Whether it's coal that does this, or they're nuclear power rods, or they're like a dam where it's just water running through it, or a windmill with that, any of those use exactly this. This idea of electromagnets and the fact that we can spin the magnets around these coils. Now, in that, what is this fan called by real name? This is my turbine. Okay. We did not write almost anything down with that. I'm okay with it if you're okay with it.
I like it.
Just talking about it, if I ask how is power made, turbine spins with magnets around a coil. That's it. Like, that's a basic idea. The stronger the magnets, the stronger the current. The more coils, the stronger the current. There's a lot of things that can go into this. Okay. Now, as we look at this, this is a basic idea. There's two types of energy and currents that we've talked about already. And this is just going to be a quick, tiny section. What are the two types of current that we've seen?
Generator.
So generators make current, for sure. What do these stand for?
Alternating current and direct current.
Alternating and direct. What's the difference? What does it mean to alternate?
Alternate back and forth.
Wiggle, 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 right? Okay, so for this, I'm just going to say wiggle. And it wiggles at a particular speed in this country.
60.
60 what?
Hertz.
Hertz. Okay, it wiggles back and forth. Because all of you requires electrons moving through. It doesn't matter if they push through and keep going or if they wiggle back and forth. You're still getting electrons moving through something. Okay, that's the alternating part, right? Wiggle. What's the direct mean?
It's direct electricity.
Straight through. So when we did that lab, and I know that I'm going to ask you to like dig deep in your memory, you can see the electrons flowing through the wire, right? Were we looking at AC or DC?
DC.
We were looking at DC because an electron starts and it goes and then it comes out the other end. That is direct. Now, anything that you plug in to an outlet in your house, alternating current. We use AC because when we spin that magnet, it produces an alternating current as that turbine moves. If a battery is used, is there any magnet turning inside of a battery, you think? So what sort of current do you think we get?
DC.
DC is batteries. Okay, unless you have something specific to switch it, but that's beyond what we're looking at. Okay, I'm going to keep referencing that electricity lab. Why can't I have a single big solar farm in Arizona that powers the whole country?
Because we have
we don't have a
What's a superconductor?
something that travels through with no resistance.
Okay,
Energy that travels.
wires have resistance, right? Yep, sign on the sheet. Wires have resistance, which is like friction. Do we lose energy due to friction?
Yes.
Does electricity lose energy due to resistance?
Yes.
And it turns into heat is what winds up happening. Now, we have a fundamental issue. We don't have to go very far from the powerhouse to here, but it's probably like a mile or so, maybe a mile and a half if you count, like looked at the wires running underneath the ground. If you want to push something a mile and a half, even a ball, you have to push it really hard,
Yeah.
right? Like, really hard. What's the idea in electricity that's like how hard it gets pushed?
Potential difference.
It's our difference, our potential difference. Give me another word for it.
Voltage.
Voltage. If I want to take current from that powerhouse over there and get it to be pushed all the way to me, do you agree we need a very, very high voltage? Okay, now high voltages wind up producing really high currents. If I have a high enough voltage to push the electricity from the power plant to here, do I need that same voltage in the wall? No, it's going to explode anything that I plug into it because we don't have wires that are this thick to move electricity throughout our house. There's an issue. We need to up the voltage when it leaves the power plant, then we need to bring it back down when it gets here. Okay, I talked about these the other day. If you haven't seen it, there's a green, not the otters. There's a green box over there.
pointing to the
I'm still pointing at the otters. Everybody stand up real quick. We're going to look out this window. And you'll see it. You're not looking at the otters. Go look across the street. Just make sure you can see the green box I'm talking about. Somebody said they like to lay on them.
Oh, that one.
Okay, there's, even if you have bad eyesight, can you tell there's a sign on it?
Yeah.
Says do not touch.
It said, does it really? I can't see it. But it shows me like I'm going to die if I do this. What's inside that green box?
Oh, it did.
It shows the little guy with like a lightning bolt going through him.
Okay,
There's
so
a face right there.
danger is an easy answer, right? Like if you're not qualified, you want to see what they're looking at? You see the green boxes over there? You can see them all around town at the bottom of the light pole. You see the big red and like even if you have, you see the sign on it that's looking at like kind of ominous? It says warning, don't touch this. Okay, now in there is something very specific, and whether that particular one has it or not, it's hard for me to tell, but I would guess that it is. Within every single one of those boxes that you're looking at, and this is pretty close to our last big idea, is what's called a transformer. Okay, so real quick, it's not Optimus Prime, it's not Bumblebee. We are transforming, but not robots and Decepticons, and I don't. Yeah. You guys know what Autobots is for?
Autobots for the good
roll
guys.
out.
What's Autobots like? Why is it called an Autobot?
Automatic bot. I don't know.
Autobots roll out, you know?
They do roll out autonomous robots.
Autonomous Prime.
Yeah, less cool. Less cool. All right. When we talk about Transformers, there's a whole movie franchise around robots that do this, but not what we're talking about. Transformers with electricity. What do you think they're transforming? So we're back to electricity. What did we say a second ago was the issue with getting power from there to here? The resistance. So you got to push really hard. And what's the push in electricity? Transformers increase or decrease voltage?
Transformers, why would
not of, or decrease voltage. All right, so I'm going to give you guys a small little challenge here. We're not going to quite finish today, but I'm going to make a picture here for you. There's two ways that we can do this, voltage of AC. Now, this is what I would write. When I say these increase or decrease voltage of what? So give me the words. Alternating current. We need alternating current for these guys. All right. I want one of two things. Either I produce energy and I need to up the voltage to be able to push it further, or I need to bring it back down to be able to use safely here, because different size wires. As we're looking at this, there's two different ways, and my guess is you'll be able to knock this out pretty easily. We have two types of transformers. It is either a step up or a step down. I wish it were Optimus, and I don't know the name of a Decepticon. Cool. Okay. These do similar but exactly opposite things. What do you think a step-up transformer does?
It goes up.
It brings the
Voltage up.
Voltage up. Cool. I don't know that that's true, but I don't remember what you said either. What's a step down do?
Probably bring down the voltage.
Seems reasonable. Voltage down. Okay. I'm going to show you, and I'm going to draw one, and I want you guys to draw this. It doesn't have to be perfect. Okay. We're going to draw a small transformer. So inside, not the robots. Inside of those boxes, this is a simplified version, but I'm going to draw a small square. And you obviously, I assume you're not going to color yours, but you might. I'm going to hollow this thing out because metal's expensive. So all I have here is a chunk of metal that's in the shape of a square, but it's hollow in the middle. I'm going to put Fe on this. Why? What's Fe?
iron.
Iron. Anything special about iron?
If it moves quick enough, it's magnetic.
It can become magnetic really easily. Like iron nails are what we use as our cores here. So, check this out. All we're going to do is I'm going to use colors for mine. You do not have to. Let's say that I have this big chunk of iron that has a hole in it. And I have current that comes in and it coils here. I have a lot of practice. Okay. Quick question here. Something's backward there.
Yeah, the last one.
Yep.
The last one.
Thank you. Cool. Okay. Two things that I want us to think about here. Let's say hypothetically I'm somewhere and I have energy coming in here. So this is called the load side of a circuit or of a transformer we could look at. I'm going to say that this voltage coming into this little square thing and wrapping around it and then leaving again is, let's say, 300 volts. Okay, pretty powerful at this point in time. What we have here is the energy, the power, everything coming in. We're going to say that this coil right here, which it is a coil, this side is what's called the primary coil. Cool. All right. Now, I have 300 volts coming into this thing. Hypothetically, let's say that on the other side, I have a few more coils. And how many turns did you see me make around this? 1, 2, everybody agree there's 3? So this one I'm going to draw with 6. I'm just going to draw twice as many. So there's 1, 2, 3, 4, 5, and 6. So 3 and 6. Now, as we do this, let's just think about little bits and pieces of it. Forget about the entire right half. You don't have to erase it, just forget about it. I have current moving around a piece of iron which has formed a solenoid. What does it make this iron turn into if we run current in a coil around a piece of iron? It turns into a magnet. Now, we have alternating current, which means it's going from north to south, and it's switching, right? Okay, this whole piece of metal is a super strong magnet. Everybody cool with that? On the other side of this, I have another coil that is now working within a magnet that the field keeps switching.
Wait,
When this field switches back and forth on this big piece of metal, what does it cause to happen in this coil? So it could be positive and negative. What happens when we spin a magnet around the conductor? The electrons move within this one, which causes what? If we spin a magnet around the conductor, like we looked at with the generator, what's it making? Electricity, right? So here's where we're going to pick up tomorrow. We have current coming in, making this thing a magnet, and then we have stuff leaving afterward through that magnetic field. As we look at it, here's the really cool part of this. We're going to jump in here because people are already packing up and I want to make sure we get it. Cool. What's today, Wednesday?